We're going to work through problem 4.17 from Taylor's Classical Mechanics. This is a chapter 4 problem on force as the gradient of potential energy. So in this problem, they're telling us that we have a charge Q and it's sitting in a uniform magnetic field. What that means when they're saying the field is uniform is that it doesn't vary. So that means that it is constant. It experiences a constant force, F equals that charge, times our magnetic field, or electric field actually. And we want to show that this force is conservative and verify that the potential energy of the charge at a position R is negative Q E naught dot R. This is what we're trying to show. Okay. So this is part A. We're going to try and show that that is our potential energy of the charge at a position R. So we know our force. Using our force, we can find the work. So the work is going to be the integral of that force dotted with dr, which in our case, it's going to be the integral from R1 to R2 of Q E naught dot dr. And because our Q and our E naught are constant, our charge isn't varying, and our field is uniform, you can pull those out. And that just leaves us with R, and we're going to go from R1 to R2. So this is going to be Q E naught R2 minus R1. That is going to be our work. So using the work, we know that for a conservative field, the potential is going to be the negative of that work. This is only for a conservative field, however. Now, as you can see, this is independent of path. It only depends on the final and initial positions. So our force is conservative. So we're able to use this formula to find our potential function. So U of R is going to be the negative of our Q E naught R2 minus R1. If we assume that we start from a zero vector as our initial, this leaves us with negative Q E naught dot R2, which we can just call R. So we've completed part A. We've shown that that is the potential. That matches exactly what they gave us. Now for part B, we want to check that the force is the negative of the gradient of that potential. So for part B, we want to confirm this. So our potential is negative Q E naught dot R. If we want to take the gradient of our potential with respect to R, you can turn this into X, Y, and Z and then take each component that way. When you take the gradient though, with respect to R, that just gets rid of the R. And if we take the force is the negative of that gradient, you can quickly see that our negative is going to go away. We're going to end up with Q E naught is our force, which is exactly what they gave us to start with. And that completes the problem.